including the Wednesday before Thanksgiving. I don't know if we should take that one off. But it's not a holiday. But if you all agree, you can take it off.
Yeah, I won't be here.
Oh, you have decided.
Well,
So
just saying.
some of you have decided not to come anyway.
Well, okay, I didn't decide it. It was a family
Well,
decision.
if I come here, I don't see anybody. Then I can walk away.
Exactly.
But if there's one person here.
No, I'm not saying don't do it. I'm just saying I won't be here.
Anyway, we can decide later. Okay? So, let me review what we did last time. What is the status of your lab? Done?
We have one.
Oh, wait, yeah, one section is behind, so we have one more.
One
So.
more. Okay. Are you measuring the frequency response yet?
That's the last
The
one.
last one.
So we have not done it yet.
Okay. So let me guess. You're gonna have a circuit, right? You're gonna put some frequencies as the input, and output. You're gonna look at the frequency response, right? I hope. And you're gonna have to use. You're not gonna use oscilloscope because oscilloscope give you the time domain result, right? You're gonna have to look at the spectrum analyzer. True or not? Well, there must be an equipment that would allow you to look at the performance versus the frequency, which is called the spectrum analyzer.
Your lab says they pretty much just find the minus 3 dB point by just changing the frequency generator and just manually changing the frequency until you got to the minus 3 dB point.
Oh.
Kind of.
Also, you still look at
It's manual.
the waveform of the oscilloscope.
Yeah, but you just change the input frequency.
Okay.
It's cheating, but.
Well,
We did simulations with
okay.
AC analysis and all
I
that.
feel like it's kind of the
I
opposite.
guess
You're like doing it manually.
It was the spectrum analyzer, unfortunately. Yeah, which is more expensive. All right.
It's just really
So
disappointing.
let's say you have a circuit, right? You have the input, we call it this line. You have the output voltage, we call this one, right? Okay. Now, if you want to do the frequency analysis, you're going to have to convert the circuit to the S domain. Yes?
Is this similar to the transfer function? You gotta do.
Yeah. So basically, in the S domain, your R is still R, there's no change. Your C becomes 1 over C. That's it, right? So we are not talking about inductor, right? So I'm not going to mention about inductor, right? If you have inductor, of course, it becomes cell, right?
Yeah.
Okay. Then, once you have done that, all the components are like resistors. Huh? Okay. So then you can divide A sub B in S domain. Sometimes it's called transfer function. Okay. Okay. So this A sub B, of course, it should be a function of S. Can be something like something like this, generally speaking. So basically, you have a polynomial on the top. You have another polynomial on the right. Okay. Again, generally speaking, right? So basically, this can be break down into several different components. You can have a constant. You can have S. You can have S squared. You can have 1 plus S over some K. Okay? mean, this can be the product of those. Okay, so there are different components you can have from the polynomial, right? Well, basically, if you look at this is what you have, what you should expect. You should expect 1 plus s plus some constant, s plus another constant, correct? Because it's a quadratic equation, right? Okay, but from this, in order to do the polyplot, you should make it 1 plus sk1. This one, 1 plus sk2. Okay, that's what we call the standard format for polyplot. But you can just do like this, right? You have to do what? Correct? You have to multiply this, yes? Okay? So therefore, this would have 3 components, right? Constant, right? This is a constant, correct? This is like this, yes? And this is like that, correct? So generally speaking, you have this type of components. Okay. So now I'm going to just tell you how you can do the polyplot for those components. Yes? So if you have a constant, and you want to do the magnitude polyplot, so basically what you're doing the 20 times log n of the constant, right? That's what you're doing. So, and when you do the plot, you'll be just a constant, right? Versus omega. And this is the ACB in dB. Yeah? By the way, this is the log scale, and it's the linear scale. Okay, so that's one. The second one is an S, right? So basically what you're doing, this is 20 log 10 of the magnitude of S. And remember, S is j omega, right? So what is the magnitude of j omega? It's omega, yes? Okay? Then, you do the plot. Let's say this is 1 and 100,000. This is 0, let's say 20 dB, 40 dB, etc. You look at omega equal to 1, log 10, 1 is equal to 0, right? So you always start at this point. At omega equal to 1, we have 0 dB. With omega equal to 10, log 10 of 10 is 1, so it becomes what? 20. So 40, right? So that becomes what? There. So this is a slope, 20 dB per decade. Yes? So every time you see an S, that is the curve. Now, of course, you can also have 1 over S, right? S could be the numerator, in the denominator. So this is the case of S in the denominator. Then you're doing what? You're doing the 20 log n of 1 over S, right? Or 20 log n of 1 over omega, right? Because you're taking the magnitude. Okay, according to the log log rule, okay? Log 10a over b is what? A minus log 10b, right? So therefore, therefore here we have log 10 of 1 minus log 10 of omega, correct? This is 0, right? Because log 10 minus 0. So therefore the end result is minus log 10 omega. So the difference between here and here is that this is positive and this is negative.
Shouldn't there be a 20 log?
Negative
20 log?
Then, instead of a positive 20 dB per decade slope, now you can see a minus 20 dB. Going to the same point. Okay, 1 and omega equal to 1 is 0 dB. Okay, so go. Right? This one. That's minus 20 dB. So this one, I mean, this is plot of S. This is the plot of what? 1 S. Yeah? Okay, then you say, what about if I have S squared? What do I do? So simple. If you have S squared, then it's S times S, right? Okay, so you're talking about 20 log 10 of S times S is equal to 20 log 10 of omega times omega, right? Because omega is the magnitude of S. Okay, then according to the logarithm function, log 10a times 3 equal to what? Log a plus log 10b. Got it? So what does that mean? S squared is what? Yeah, it's log S plus. So if you do the plot, what is the difference? It's twice, correct? So the slope becomes what? Okay, again, we have to go through this point, huh? 0 dB. But now the slope is what?
40.
Yeah, 40 dB. Okay, so this is the plot of 1 over plot of S squared, correct? Because it's twice, got it? And then we have the reverse, minus 40 dB per decade, if we have what? 1 over S squared, yes? Okay, the last component is last one is let's say you have 1 plus S over K, right? Okay, then you're doing the log 10, the magnitude of 1 plus J omega 10, correct? So therefore, it's 20 dB, 20 times, equal to 20 log 10, right? Of the square root 1 plus omega squared 100, correct? This is a complex number, right? The magnitude of that complex number is that, yes? The square root of the real square, 1 square, and the imaginary square, yes? Okay, so there are two cases. If omega is much less than 10, this is 10, right? Much less than 10, then you are looking at omega log 10 of 1. Yes? Correct or not? If omega is much less than 10, this term becomes much smaller than 1. So you're looking at 20 log 10 of 1, which is 0 dB. Right? If omega is much larger than 10, then 1 becomes insignificant, right? So you have 20 log 10 of 1. This one becomes much smaller, so it becomes omega over 10. All right? Okay, then now you can do the plot, the symmetry, the asymptote. Yeah? So A sub B versus omega. So let's say this is K. Where do I have a 10 there? Oh, I assume K equal to 10, okay? That's what I did. Okay? So you may wonder why is it? In general, this should be K, okay? Right? Okay, I put a number. So that's K, and I put K equal to 10, okay? So if you look at these two extreme cases, for omega much less than 10, you have what? 0, correct? Okay? For omega much larger than 10, you have this. This means you have a slope of 20 dB per decade. Right? So these are the two extremes. Now, when you try to plot the asymptote means approximation, okay? Then you just say, okay, it's all the way to here, 0, and then after 10, you have a slope of plus 20 dB per day. That's the asymptote. Now, if you want to be more accurate, then it should be like this, yes? Like this, huh? There will be a curve right here. And the worst case between the asymptote and the real is here. And that difference is 3 dB. Got it? So the difference between the real, the actual plot, and the asymptote at K equal 10 is 3 dB. So therefore, this K, sometimes called the 3 dB frequency. Got it? And I like to call this as the corner frequency. Some people call this break frequency, so they have different names. Okay. So it doesn't matter which one you choose. Huh? It's the same concept. All right. Now, if you have 1 over that function, I don't think I need to get into detail, right? If you have 1 over 1 plus s over k, yes? Then it will be like this. This is k. So it will be like this, and then go down. Right? Minus 20 dB per sec. That's it. So this is the fundamental of body part. So now I'm going to start to do many examples, okay, based on this concept. Okay. So let's do a simple example first. It's just an RL circuit. Okay, so let's say in circuit like this. And by the way, this circuit is called the high pass, low pass, I'm not sure. This circuit is probably called it's probably called a high pass filter. And I will explain this later. Okay, so first of all, you have to convert the circuit into the S domain, right? So therefore, this becomes 1 over SCS, right? This becomes VIS, this becomes VOS, right? That's it. Okay, then you proceed to derive the voltage gain of the circuit, yes? Which is pretty simple. So VOS, look at the circuit, huh? Is equal to VIS, right? Times RS plus RP plus 1 over SC over, on the top is RP, right? It's a voltage divided. So therefore, the voltage gain in the S domain is RP over yeah, but in order to do the Boyle plot, right? We have to put this into the standard form. This is not a standard form. How are you going to do the Boyle plot? You cannot. So what do? The first thing to do is what? Is to multiply SC on top and SC on bottom. Yes? Okay, so RP SC, right? And then RS plus RP SC plus 1. But this is, huh? Correct or not? Okay, so therefore, this is a constant, right? So RP, RS plus RP, right? Times SC 1 plus SC, CS, correct? Am I doing this correctly or not?
No. The one will be over RS.
Take the RS, start the out from the bottom.
Gotta divide the one.
Huh?
Gotta divide this one right here.
The one is to be
This
divided
one?
by
With 1 over RS plus RP.
1 over, oh, 1. This is what? No.
You can
What?
take
The bottom
you take
one.
the RP off the top. Bottom, you have to divide with 1. You want to factor it out.
You didn't factor the 1.
Okay. I see. Okay. So let me do this SCS RS plus RP 1 plus SCS RS plus RP. Yes? Correct? Okay, now you can see we started to see the standard form being shaping up. Yes? Why? How do you put this into standard form? Basically, this and that is a constant, right? So I'm going to call this constant K1, can I? All these are constants, right? S on the top, yes? And then on the bottom, I have 1 plus S, right? Because I want to put 1 plus S over something. And constant 2. Got it? Correct? So now the question is, what is constant 2? Huh? What is K2? K2 is 1 over CS RS plus RP. Is it correct or not? Hmm? Okay. So from here, you should know what is the shape of the body plot. What do you think? You have a constant, right? So constant. You have an S, correct? Yes? 20 dB per decade, all the way. You have this. So let's say this is K2, correct? 0, and then up or down? Down, yes. Minus 20 dB. Yes? So the final shape should look something like this, right? Until here, like this, and then like this. Huh? Okay, I'm just approximation, okay? So now I'm going to plug in the numbers to give you the precise plot, okay? And so I have to give you some numbers now, okay? So let me give you RS equal to 1K, R sub P is equal to 10K, C sub S equal to 1 microfarad. Right? Okay. So with these numbers, you're going to find that VAB
Shouldn't it be a straight line after K2?
yes? What?
The plot, shouldn't it be a straight line after K2? There's only one here.
Should there be a what? Anyway, let me do this example, it'll be easier to see, okay? Yeah. So after you plug in these numbers, okay, you use this equation, got it? Okay, you use the expression, you plug in numbers, that's what you got. Okay, 0.9 times 1.1 times 10 minus 2s on the top, 1 plus s, 1.1 times 10 minus 2 on the bottom. Yes? Okay. So, now, of course, I'm going to combine this, right? So that I can do the plot easier. So what is the combination with that? That is about equal to. This is about what, right? 1. So it's 10 to the minus 2 s. Yes. 1 plus S. What is that? This is 1 over 1.1 times 10 to the minus 2, correct? So I would say it will be about equal to 100. Agree or not?
Yeah.
You see, once you have this form, it is very easy to put the body part, right? As I told you, there's a component which is a constant. You have an S. You have 1 plus S over constant, right? So go ahead and do the plot. Omega A sub B 20, 40, 60. This is minus 20, minus 40, minus 60, right? Okay. And then omega, you can say 1, 10, 100, 1,000. Okay. Like this. Of course, the unit is in the radian per second. This is dB. Yes. Okay. So the first component, 10 to the minus 2. So we are talking about 20 log 10 of that. So therefore, it's what? It's minus 40, right? So that's the first component. Yes? 20 log 10 of that is minus 40. And then an S. Now you know how to do that, right? So that's component number 2. Right? It has 20 dB per decade slope, and this curve must has 0 dB at omega equal to 1. Right? Because you can have the same slope, and you can have it parallel anywhere, right? You must go through 0 dB at omega equal to 1. Okay, the last one. You have the rate frequency, right? Corner frequency, 100. So it will be 0. And then, right? So it's number 3. Okay. The final plot will be the summation of the 3. Okay? So if you want to start from here, what is the starting point? Minus 20, 0, minus 60. So the starting point is minus 60. Yes? Correct? And then once you have the starting point, you just follow the net slope. Net slope. So from here to here, your slope is not changed, right? So you have minus 60 all the way, one decade, 2 decade, 3 decade. That means what? It's going to go all the way to 0 dB, right? 3 decades, the slope is 20 dB, right? So therefore, you can go from minus 60 to 0. Basically, it's the net slope. What is the net slope? 0, 0, 20, right? So the net slope is 20 dB per second. And then, between here and here, it becomes what? It becomes flat, right? No, flat. Why? You have plus 20, you have 0, you have minus 20. Yeah? So the slope is 0. And then after 1,000, you have plus 20, 0, the same, huh? No change. So the reason this circuit is called the high-pass filter is because what? Because for signal with high frequencies right here, right? High frequencies, you have a small gate. For the signal with low frequency, you have no gain. If you have no gain means when the signal is going through the circuit, will be dropped. Huh? So that means the high frequency can pass, the low frequency will drop. Okay, so this is the conventional way to analyze the frequency response of the circuit. Now, I'm going to give you a shortcut. And I'm going to use the shortcut for the rest of the chapter. I think you're going to like the shortcut much more than this. So the shortcut. Okay? First, you derive A sub B by assuming ideal capacity. What do I mean ideal? Ideal means when C is in series, it is short. When C is in parallel, it is open. Now, of course, in order to make the assumption more reasonable, this C must be what? C must be relatively large, yes? Because it's going to be short. And this C must be what? Relatively small, correct? So this is the restriction of the shortcut. Okay? When you have a C in series, the value of the C must be relatively large. When you have a C in parallel, the value of the C must be relatively small. So this is the conditions. Okay. Then if you look at the circuit, what is A sub B? I would call A sub B ideal, did I? It's simple, right? R P over RS plus RP. So if I use the numbers I gave you, this is 10 to the minus 2. Okay, second, find the RC time constants associated with the capacitance. Okay. So you look at the capacitor, right? This is a input RS, CS, RP, correct? So you've used the Thevenin approach. You can take this out, right? And you want to look into the equivalent circuit from these two terminals. Now, of course, when you put Thevenin, what happened to this one? This is short, right? Okay, so basically, you will have capacitor, R sub S, R sub P like this. Yes? And these two, as far as the capacity is concerned, these two are in series, right? So therefore, top, which is called the time constant, is equal to what? C sub S times R sub S or R sub P. Yes? That is the time constant associated with the capacity. Then, the what do I call the corner frequency, omega omega is equal to 1 over tau. That's it. So it's equal to 1 over CS RS plus RP. Okay, and then if you plug in the numbers I gave you, that is about 100 radians per second. All right. With this two information, you can go ahead to the body clock. Right? Okay. Yeah.
RP over S plus RP equals to 1.
Huh?
Would be 10K over 11K.
This one? Oh. It's 10 to the minus 1, you say?
It'd be just 1.
Just 1. Okay, that's fine. That's fine. Okay. Thank you. Is this one correct? CS, that is about 100. Okay, so first thing you do, you mark the corner frequency, right? Correct? Okay? And then you take this one, you do the 20 log 10 of that, which is what? Which is 0 dB, correct? So this, all the way, this is called A sub B ideal. And then at 100, it has a break. So you put a minus 20 dB. Actually, it's plus 20 dB if you go this way up. That is exactly what I have. Right? See how long does it take for me to do the shortcut? 5 minutes. It took me 20 minutes. If you only use the traditional approach. Got it? Okay, let me do more example. Okay, so now I'm going to do a low pass filter. Okay. The one we just did was a high pass filter. So let's do low pass filter. Okay. Okay, now let me go through the traditional approach one more time, okay? So if you want to derive A sub B in the S domain, right? Then this becomes what? 1 over SCP, correct? All right, then how do you do? What do you do? You can use the nodal analysis, right? There's a node here. So you have VO minus VI over R space plus VO over RP plus VO over 1 over CP equal to 0, correct? Huh? Oh, 1 over S. 1 over S. Okay, then you have to do a lot of algebra, okay? I'm not going to do that, I will skip. So at the end, you get something like this. this will be the form that is suitable to the Bode plot. Yes, because you have a constant, right? You have this is 1, and then you have 1 plus s constant, right? Okay. So now let me use the shortcut, right? Basically, when you look at this, you should know what you look like. Huh? Constant will be constant, right? This one, 1 plus s over something. Yes. So you will have a break corner frequency, right? And then because it's in a manner, so it's going to go down, right? So at the end, this, that's what you should expect. And this is called the low pass. Why? Because the high frequency signal will drop, right? The low frequency signal will be passed. Okay, so now let me put in the numbers. The same RP and RS. What do I have to give you? RS 1K, RP 10K, okay? And then CP go to 3 picofarad. So if I do this, if I plug in the numbers, I will get VOVI equal to about 1 times 1 over S 1 plus S over 3 times 10 to the 8. Okay? So apparently the corner frequency will be how much? 3 times 10 to the 8, correct? Okay. Now I'm going to do the shortcut. Okay? So I go to the shortcut. The first one is to derive A sub B ideal, correct? And this time we have the capacitor in parallel, yes? So we're going to assume it's open. Of course, we have to use the condition C is small. And if you look at the value I gave you, C is quite small, right? Pico. Okay. So what is A sub B ideal if the capacitor is open? It's very simple, right? It's R sub S plus R sub B and R sub B, correct? Okay. And then if you plug in the numbers, that's 1. Y equal to 1. Okay. 2, I need to find the RC time constant. Top. Okay, so what is top? So basically you open up on both ends, right? So here, what do you have? You have R sub P, you have R sub S, and this is short, right? Because when you do the Thevenin equivalent, R sub I must be disabled. And here on the right hand side is open, right? Okay, so that's C sub P. Okay, so on this side, what do you have? On this side, you have R sub S in parallel with R sub P, right? On the other side, it's infinity, right? So therefore, tau is equal to C sub p times RC time constant, huh? R sub s for R sub s in parallel with R sub p, correct? On one side. Plus infinity on the other side. Right? So we're going to do this, okay? So at the end, this is R sub s in parallel with R sub p, correct? On this one, it's infinity, yes? So as far as the C concerned, these two are in series. So they are adding. And then multiply with C. That's it. That's the RC time constant. Of course, if it's infinity, it doesn't matter, right? My English right or no? Maybe it's in parallel, huh? It's in parallel with infinity. Anyway, when you see one side is infinity, then you don't have to include it, right? It's just one. Just include this side, that's all. Okay, so it's CP times that, yeah? So what is the value of that? I can bet with you that value is the same as what I gave you there. 3 omega, huh? So omega is so omega is 1 over tau and is equal to 1 over CP R S in parallel to RP. And that, if you plug in the numbers, you'll find that it's about 3 times 10 to the 8. All right? So now you have this two information. You can go ahead and sketch the body plot. Omega, A sub B, right? So 3 times 10 to the 8, yes? A sub B max is here. Yes? This is A sub B ideal. Sometimes it's called A sub B max because it's always the maximum value. Okay? Is it 0 dB? Huh? Right? Why? Yeah, because A sub B equal to 1. Yes? 1 is 0 dB. Okay. So what you do is you put it straight, right? 0. And then at the corner frequency goes down. Okay, you ask me why it doesn't go up. Huh? In the real circuit, it's always going down. And A sub B ideal is always the maximum. Okay? So therefore it cannot go up. Okay, then you can ask me, what happens if I have two corner frequencies? Huh? You can. Let's say, okay, as a assumption. Let's say I have another corner frequency right here. Huh? Then what happens is that at this corner frequency, this will drop even more. Okay, by another 20%, by another 20 dB per decade. So this slope will become minus 40. Got it? Now what happens if I have a corner frequency here? Then it will drop this way. Yes? If I have another one here, got it? That's the concept. So remember, every time you have a capacitor, you have a corner frequency, right? So if you have this, that means the circuit will have how many? You have 4 capacitors. Later on, we're going to do some circuit that has 3 or 4 capacitors. That's what you see. Right? You say, okay, then what's the purpose of this curve, huh? Oh, it tells you lots of stuff, right? For example, let's just forget about all this, okay? Just concentrate on this one, okay? Just concentrate on that one, okay? This one will tell you that if you have a signal that has a frequency below 3 times 10 to the 8, your current, your voltage gain is what? Is 1, right? That means whatever the voltage you put in, you will get the same voltage out. Yes? Okay. When omega is larger than 3 times 10 to the 8, the magnitude of the voltage you put in will become less at the output. How much less? How much? Depends on the frequency, right? Let's say if I give you an example, let's say if I say 10 to the 3 times 10 to the 9, then what is the voltage gain at 3 times 10 to the 9? It's 1 decade above, right? When you have 1 decade above means this will be dropped by how much? 20 dB, right? So therefore the A sub B will be how much? You will drop from 0 to here, so it's minus 20 dB. So in the real number, what is it? 0.1, right? So at omega equal to 3.9, the voltage gain will be 0.1. That means if you put a signal, let's say if your V sub I is equal to 1 millivolt, then what is V sub I? And here, 0.1 millivolt, right? Okay. Let's say, what about at 10 to the 9? At 10 to the 9 is not exactly 1 decade, correct? So what do? Well, you can use the octave. So 20 dB is the same as minus 6 dB per octave. Octave is every 2. Got it? 2. Okay. So let's see if we can do this, right? So what is the next octave? Huh? 6, right? Correct? 3, 6. The next octave is what? 12. So 1.2. So you have 2 octave is 1.2 times 10 to the 9, right? Which is quite close. So we can do that. Yes? So what is at 1.2 times 10 to the 9? Huh? Minus 6. Minus 6. So it's a what? Yes? And minus 12 dB can translate to the real number. Probably 0.3 or 0.4. Right? Let's say if I want to do 10 to 10, right? 10 to the 10. Well, 10 to the 10 will be 1 decade beyond that. Yes? So this is minus 12. So 10 to the 10 must be what? What? Correct? Because it's minus 20 dB beyond that. So it's a minus 32. So you got to be able to read this curve, right? Okay. Now let's move on to the next circuit. What I'm doing now are just RLC circuit, right? Well, actually not RC circuit. So later on we'll do the real circuit, okay? So let's do a band pass filter. So a band pass filter will look like this. Okay, I'm going to skip the traditional approach, okay? And I'll go strictly to the shortcut, right? Believe me, the shortcut will be much easier. So for the shortcut, what do you have to do? First, you try to find A sub B max or A sub B ideal, right? By assuming CS is what? Short, CP is open. Okay? Then A sub B max becomes R sub P over R sub S plus R sub P, right? Okay, second, find two RC time constants. Why do we have two? Because we have two capacitors, right? Okay, so if you look at CS, right? Basically, we have yes. Then your time constant tau associated with CS is equal to CS times RS plus RP, right? Okay, the other time constant, so this is omega CS 1 over CS RS plus RP, right? So that is one of the corner frequency resulting from CS. Okay, the second one is CP, right? So for CP, this is what you have. Right? CP. So on the left hand side, you have CS integral is RP. On the right hand side is infinity, right? So therefore, tau CP is equal to CP times RS integral with RP. Actually, integral with infinity, but it doesn't matter, right? Okay, so omega CP will be 1 over that. Yes? All right, now, if we use the same values as before, you know, RS, I forgot, 1K, RP equal to what? 10K, I think, right? RS equal to what? Something? 3 microfarad. RP equal to what? 10? 3 picofarad. 3 picofarad, right? Like that.
CS.
CS, right? Something like that. Then AB max is 1, right? Omega CS is 100, I think. Omega CP is 3 times 10 to the 8, right? By the way, the unit for this is radian per second. You can change it to frequency in hertz if you like, right? You know, omega is equal to 2 pi f. Okay, sometimes the problem will actually to plot the body plot versus frequency hertz. Okay, then you have to do the conversion. Okay, and so you have basically ACB max here, right? Okay, then you have corner frequency 100. You have one much higher, 3 times 10 to the 8, right? So this one drop this way, this one drop the other way, right? That's it. And then between these two is flat. So this is called the bandwidth. The bandwidth, of course, is equal to what? Omega Cp minus omega Cs, correct? So this is omega Cp, this is omega Cs. But since this one is always much larger than that one, and much lower than that one, so it's about equal to omega Cp. Right? The lower boundary of the bandwidth is always much smaller than the upper boundary. So sometimes you do your homework, the homework will say, okay, design a circuit that has a bandwidth equal to something, then you should know that that something will be the upper boundary of the plot. Okay, let's stop here. Do you have any questions? So we have done all RC circuit. Next time we're going to start to do the enterprise.